Hello guys, this is Assistant Professor from Institute of Engineering and Technology. Today we are going to study about the effective mass and Fermilevel. So let's begin. Now, effective mass of electron. Conceptually, what is effective mass of electron? The alternate mass of electron due to the periodic potential in a crystal lattice is called as effective mass of electron. So basically what happens in our case, when electron is kept in vacuum, okay, and when you give the sufficient energy, it would be moving from one position to another position, okay. So only at present one field is working, that is our electric field, okay. But practically when we keep that in our lattice structure, what happens? Two field actually affects it. First, the electric field that we have given, as well as the potential field that is by the lattice structure. So when this two force affects, the effective mass will vary little bit, okay. So in vacuum as well as in lattice structure or lattice structure, we are saying both would be the same effect, okay, but the additional effect is of that potential given by the lattice structure that is having, okay. How it is affecting, let's see. Now the periodic potential in lattice is as when electron is moving throughout the lattice structure, okay. So you can see that the positive and positive ends are there. So when it is moving from that part, as it is near to them, the potential would be 0, okay. But as it moves away slowly and gradually, you can see down into the graph, what happens? The potential increases. So as it moves away, potential increases and reaches to max at the middle. And again when it starts moving towards it, the potential will decrease, and this is the periodic function that will you get, okay. So this effect, the periodic effect on that electron flow, is what we are supposed to study, because this effect would be not there in the vacuum, okay. So you can see that with the help of the EK diagram that the potential is in a wave form, okay, or you can see that it is in a periodic manner. So we are with the help of this 2 EK diagram, and in the middle you can see that the energy is with respect to time varying, okay. So now let's derive the equation. So first, derivation of effective of mass of electron. In that, let E be the electric field applied to an electron inside a crystal. So the force experienced by it would be F equals to E, that is your charge. Capital E is the field applied. That can be also equated with the help of Newton force, that is mass to acceleration, okay. So now from this we can take the multiple thing. If I want only mass, it would be E into E upon A. If I want only acceleration, it would be A equals to E into capital E upon N, okay. So this is for generalized. So if I consider in vacuum, this would be the equation, and if I want to differentiate the mass in regular or practical world, it would be M star. So we will be denoting with M star and N, okay. What will be the difference? In vacuum only one field, that is the electric field, would be affecting, but when we are talking about the M star, at that point the other potential, that is the lattice potential, would be also into the picture, okay. So let's start beginning deriving the same. Velocity of the electron wave in one dimensional equals to the group velocity of the waves representing the electrons, that we have seen in the prior image, okay. So V, that is the velocity, is equal to d omega by dk. So now the energy of electron is defined as E equals to h cap omega, okay. H cap, we know that it was derived from the Planck constant, okay, that was nothing but by 2 pi by h, okay. So now d by dk equals to h cap d omega by dk. Now when we are substituting this equation in 2, okay, so what we are getting, velocity v equals to 1 by h cap d by dk, okay. So in that, what we are changing, now we are getting the h cap we are writing in the form of h by 2 pi, okay. So you can see that now v becomes, v equals to 2 pi by h into bracket d by dk, okay. But now we will go in the terms of acceleration. See, in the first equation that we were having, that was the force exerted was E into E equals to ma. In that we need to find the acceleration first. So acceleration of the electron is defined by A equals to 2 pi by h d by dt into bracket d by dk. How we are achieving this? We are doing nothing but just replace the value of v that we have derived in the terms of acceleration. Okay, so once we get this A, so now the next step we get A equals to 2 pi by h d square E upon dk square into bracket dk by dt. Now how we have achieved this? We have multiplied that acceleration equation entire by divide and multiply both by dk. Hence we get this equation. After getting this equation, what we are doing? We are going in the term of the work energy theorem. So work energy or work done can be said as equal to d. Now what is d? D is also said that force exerted on the and whatever the displacement is there, that is of dx. So next, what was the force? We also know that force is equal to ma as well as E into E, and remaining the term dx. Dx can be also written as velocity into the time taken. Okay, the time derivative is taken. So finally we are getting dE equals to E into E v dt. So now substituting a value of v from equation 3 to here, what we are getting, d by dk is equal to E into capital E into bracket 2 pi by h d by dk into dt, where dk by dt is equal to 2 pi E upon h. Okay, so whatever the term is that present in this context, that is 2 pi E into E upon h, would be nothing but dk by dt. Now in equation 4 can be also rewritten as in the term of acceleration. Okay, so what we are doing, we are just replacing that dk by dt in our context. So now A will become equals to 2 pi by h d square E upon dk square into bracket 2 pi E into E upon h. Okay, so now we are taking all the constant terms outside, so 2 pi is taken out in the bracket. Okay, so the final equation will be 4 pi by h square into bracket d square E upon dk square into E into E. That is the sixth equation we are getting. Okay, now we know that acceleration is equal to E into E upon m star. See, this is from the starting that we have done. F equals to E into E is equal to ma. Okay, from that we need acceleration. What does m star means? M star is nothing but, here it is not in vacuum, and the two field, that is the applied electric field as well as the potential will be affecting. Okay, so now we have got the acceleration. So we are just replacing the term acceleration. Okay, so E into E upon m star, entire acceleration is replaced. Now what we are doing, 4 pi by h square can be also written in the term of h cap square. Okay, and we are getting d square upon dk square E. So when we are getting this term, and see, E into E is getting cancelled out from the same. So m star, finally m star is equal to h cap square into bracket d square E upon dk square raised to minus 1. Now this is the expression of effective mass of electron, and effect from this you can see that there is a Ek term is present. So the effective mass of electron also depends on the Ek diagram. Okay, so this is m star is being derived. Now m star would be signifying what is the exerted amount of change when the two potentials are working all together. Okay, so this was all about your effective mass. Now we are starting with the Fermi level. So before we start with Fermi level, let us go through certain definitions. What is fermion? So basically the half integers between particle like electron. So electron is actually example of fermion. Okay, which obeys Pauli's principle. Now what does the Pauli's principle say? That in the energy level from downwards, that is from the ground state, it will rise to fill up on the upward direction, and at a time only two electrons can be there which will be of opposite spin. Okay, now what is Fermi level? The highest level. So when it gets filled up, the highest level that electron can occupy absolute zero, see what we are doing, we are restricting the temperature. Okay, so at absolute zero, when electron is reaching to its highest level and it is filled up, that particular level, okay, that particular level where electron is residing is Fermi level. After that we have got Fermi energy. Fermi energy possessed is nothing but the energy possessed by the electron on that particular level. So that electron's energy that was possessed to reach the Fermi level is known as your Fermi energy. Okay. So this is fermion, Fermi level and Fermi energy. Now when we consider Fermi function, so Fermi function can be also said as Fermi distribution function, and it is all about the probability. So the probability of occupancy of energy levels by fermions in terms of Fermi energy at absolute zero and Boltzmann constant is known as Fermi function. So that Fermi function you can clearly get it from this. Okay, so there each and every point, that is, let us consider a system of electrons with thermal equilibrium at the temperature T. The probability Fe of an electron occupying the energy level is given by Fe is equal to 1 by 1 plus e raised to e minus ef, that is the difference. E is our energy, Ef is our Fermi energy, okay, upon kT. So in that, Fe stands for Fermi function, Ef stands for Fermi energy, T is absolute temperature, and Kb is the Boltzmann constant, okay, and E is the energy that has been actually applied. So this is the Fermi function. So hope you guys have got 3 points. First, what is fermions? Fermions is nothing but, one of the example is electron. Fermi level is the farthest level at absolute zero where the electron reaches. That level is Fermi level. After that, the another term is Fermi energy. So electron possessing the energy at Fermi level is your Fermi energy. Now this Fe will give you the probability function of the Fermi function. Okay, it is in context of probability, that what is the probability of electron in being at particular level, and how it is done. Let us take some examples. So the dependence of the Fermi level on the temperature of the Fermi energy. So you can also say that the temperature, okay, so Fermi level is having some effect of temperature. So what we are doing, we are restricting it. We are restricting it and we are taking the case number 1. In case number 1, at T equals to 0, okay, so we are taking absolute temperature. The E, that is E is smaller than EF. So what we are saying, see this energy levels, okay, E stands for energy levels. So we have got EF. And what is the energy levels? The energy levels below EF. Okay, so definitely what would be the scenario? It should be filled. So that is also proved. So if we are taking the Fermi function f of E equals to, and where we are getting this condition done, so what would be the condition? That E minus EF that would be getting, and that equation would be reduced as 1 upon e raised to minus infinity, and we know that is equal to 1. Now the thing is, what does Fe is signifying? Fe equals to 1. It signifies that at temperature equals to 0, all the levels under the Fermi level would be occupied by electrons, and that is what the definition of Fermi level is, that it is the farthest level where the electron is residing. So below that every level electrons will be definitely present. Now we are taking the case 2. In that case 2, that is extension of case 1 only, we are taking that case 1b. What would be the scenario? At T equals to 0, again same, we are restricting the temperature, and E is greater than EF. Okay, so what would be the scenario? We are talking about the energy level above this EF. Okay, so definitely this is the farthest level. So ideally it should be, electrons probability would be 0. Okay, so that what we will get if we get that same situation here. F of E equals to 1 upon e raised to infinity is equal to 0. This suggests that the energy levels above the EF would be having probability 0, or the presence of the probability of the electron is 0. Okay, so this can be shown in the graph also. Energy versus distance, we are taking the graph, and in that we have got the energy levels. So see, electrons are getting occupied in EF, it is the farthest level. Okay, and beyond that occupied levels, they are the empty states. That's why they say that the energy level beyond the, below the EF would be all occupied, that is probability of presence is 1, and above the probability is 0. Okay, now we are taking some another case. That second case is, now we are not resting the temperature, we are getting at the room temperature. So at room temperature, E equals to EF condition, what happens? The probability function Fe will becomes 0.5. Okay, so when it is saying 0.5, it means that the probability of occupancy is 50%. Okay, it can be above or it can be below also. So it can be present there also, it can be not present. Okay, so it is not accurate one. So we can see from it the graph, you can see that this is the ideal condition. Okay, that is Fermi function 1, and at the energy level E is equal to 0. Now in this case, what is the probability? It is 0.5. So at room temperature, the probability of occupancy of electron would be 50%. It may be there, it may be not there. Okay, that is case number 2. Now the final case, what we are doing, we are increasing temperature at very high. Okay, so at very high temperature, Fermi function falls as electron gain energy and move to the higher vacant state. So now what is happening, actually you can see from the graph. So what is happening? See, there is a graph, ideal condition T0, at that you are getting perfect 1, okay, and below the 0. So as you are increasing the temperature, so you can see that T3 is the highest temperature, then slowly and gradually T2, T1. So at T3 what is happening? The energy levels when are there, or electrons present at the energy levels, what happens? When you provide this high temperature, what will be the probability? They will get to the higher vacant state. Okay, so when they are getting the higher vacant state, what happens to the probability? So in case 3, at very high temperature, Fermi function falls as electrons gain energy and move to the higher vacant state. Okay, so you can see that as you are providing the energy would be provided to electrons, and they will go and rise up to the higher energy state and more. Okay, so probability to find them within the Fermi function or Fermi level would be reduced. So in the graph also you can see that the ideal condition T0 is equal to 1. Okay, and beyond that it is nothing but 0. But middle way, as the temperature increases, what is happening? T3 is the highest temperature. Okay, so at that time the probability graph you can see that it is very narrow. After the T2 and T1, slowly and gradually it is coming towards the ideal condition. So at what happens in the high temperature? At high temperature it absorbs energy and goes to the higher vacant state. Okay, so this was all about the Fermi level and the condition and the cases regarding the Fermi level. So hope you guys have understood this lecture very well. See you in the next lecture.